Step outside right now. Look straight up. Blue sky, white clouds, familiar, comfortable. But if you traveled in a perfectly straight line from where you're standing, not a single millimeter off course, the first thing waiting for you isn't the moon. It isn't the Sunday. It's a darkness so cold it hits negative 270 degrees Celsius. A void so empty, not one molecule of air exists to breathe, stretching on for billions of light years. Most people treat above Earth like a fixed direction, a ceiling over their head. It isn't. Your above shifts every single second. Earth is spinning. It's orbiting the Sunday. The sun is charging toward the constellation Hercules at 43500 miles per hour. The entire Milky Way is drifting through space. What sits directly above you right now is a question so complex, NASA needs pages of equations just to begin answering it. This is the absolute vertical journey through bizarre atmospheric layers, through vacuum that kills instantly, through territories of massive radiation, storms through darkness where physics follows rules that should genuinely frighten you, all the way to the farthest edge of everything humanity has ever known. Let's begin. Start here, right here at the bottom of everything. The air filling the lungs right now, the wind moving through the trees outside the clouds, building heavy and dark over the Great Plains. Before a summer storm, the sharp cold biting through the cabin walls at 35,000 feet on, a red-eye flight, all of it, every last molecule of weather and breath and pressure and atmospheric drama that has ever touched a human life exists inside a single layer that begins at the ground and ends roughly 12 kilometers above it. 12 kilometers. That number sounds significant until the right comparison arrives. If Earth were shrunk to the size of an apple sitting on a kitchen counter, the troposphere would be thinner than the apple's skin, not the flesh, not the core, the outermost paper-thin peel that barely resists a fingernail. That entire vertical space, 12 kilometers of air stacked above the surface, would vanish into something too thin to see on a scale model. And yet, that invisible skin is the complete world of every weather system, every cloud formation, every breath, every storm, every living creature that has ever existed on this planet. 80% of Earth's entire atmospheric mass is compressed into this layer. 80% of the weight, the density, the pressure of the whole atmosphere sits in this band, hugging the surface. The remaining 20% is spread across everything above, across the next several hundred kilometers of increasingly thin and increasingly hostile layers stacked on top of one another. But the bulk of it, the substance of it, lives here, close to the ground, clinging to the planet like a coat of paint on a basketball. The troposphere behaves by one consistent rule: as altitude increases, temperature drops. Not randomly, not unpredictably, at a rate of 6.5 degrees Celsius per kilometer. Every kilometer gained is another 6.5 degrees lost. At sea level, on a warm July afternoon in Atlanta or Houston, the air might sit at 32 degrees. Comfortable, humid, the kind of air that makes people complain about the heat. Climb 1 kilometer above that city, roughly the height of a small mountain, and the temperature has already dropped 6.5 degrees. Climb to the top of the troposphere, the invisible ceiling called the tropopause, where this layer formally ends and the temperature has fallen to around negative 60 degrees Celsius. Negative 60. That is not the cold of a Chicago winter or a high-altitude ski resort. That is the kind of cold that causes jet fuel to behave unpredictably, that freezes unprotected tissue in under a minute, that makes metals contract and crack under stress. It is brutal, killing cold, and it exists inside the layer that children color blue when they draw the sky, inside the same gradient of soft blue that stretches over every backyard, every beach, every open field on a clear afternoon. The warm, friendly sky of postcards and paintings reaches all the way up to the tropopause, and at the top of it the temperature is negative 60 degrees, and the air is so thin a person would lose consciousness in seconds without supplemental oxygen. Commercial pilots live with this reality every working day, even if most passengers never think about it. A standard commercial flight cruises between 10 and 12 kilometers altitude. That places the aircraft not high above the troposphere, not safely in some middle zone, but right at the ceiling of it, the top, the very edge of the layer that contains almost all of the breathable air on Earth. Passengers scrolling through movies and ordering ginger ale are sitting in a pressurized aluminum tube at the uppermost boundary of the planet's breathable atmosphere. A few kilometers higher, and conventional jet engines cannot sustain combustion. The air is simply too thin to burn fuel reliably. A few kilometers higher still, and the pressure outside would be incompatible with human survival even inside a pressurized cabin. The entire commercial aviation industry, every departure board, every runway, every flight path crossing the country, operates within a band of sky roughly as deep as the distance from downtown Chicago to its suburbs. The jet stream lives here too. That river of fast-moving air at the top of the troposphere, typically between 9 and 12 kilometers up, carries winds regularly exceeding 250 kilometers per hour. Airlines route flights to catch it going east and avoid it going west. It steers storm systems across continents. It shifts with the seasons in ways that affect rainfall patterns thousands of kilometers away. The jet stream is one of the primary engines of weather on Earth, and it fits entirely within this apple skin layer close enough to the surface that passenger aircraft brush through its edges on transcontinental routes. Now consider what else fits inside this layer. Hurricane Katrina, 2005, sustained winds of 220 kilometers per hour at landfall. A storm surge that put 80% of New Orleans underwater. Over 1,800 people killed, more than $125 billion in damage. The entire vertical extent of Katrina, from its base to the top of its eyewall, sat within the troposphere. Hurricane Irma, 2017. Sustained winds of 185 miles per hour for 37 consecutive hours, the longest such intensity ever recorded in the Atlantic Basin. Still inside the troposphere. Hurricane Dorian, 2019, parked over the Bahamas for 2 days, with winds strong enough to strip houses to their foundations and move vehicles like toys across flooded streets. Still inside the troposphere. Every one of those catastrophic events, representing the most violent atmospheric violence in living memory, unfolded entirely within the apple skin. The universe, it turns out, does not need to make much effort to threaten life on this planet. The storms that define human catastrophe, that reshape coastlines and displace millions of people, that dominate news cycles for weeks and recovery efforts for years, all of them are weather events happening in a layer so thin it would be invisible on a scale model of Earth. Whatever exists above that layer is not weather. It is something else entirely. Standing outside on any ordinary afternoon and looking up the sky seems enormous. The dome of blue stretching from horizon to horizon feels boundless, feels infinite, feels like it goes on forever in every direction. That feeling is an optical illusion produced by the curvature of Earth and the way sunlight scatters through those few kilometers of nitrogen and oxygen. The reality is that the entirety of that blue dome, every shade of it from the pale horizon to the deep overhead, is contained within a layer that would not even register as a line on a globe drawn to scale. It is the whole world, and by what lies above it, it is almost nothing. But just above this layer, something thin and silent waits, doing exactly one job, with no redundancy, no backup system, and if it disappeared in the next 24 hours, life on the surface of Earth would end. Cross the tropopause, that invisible boundary 12 kilometers up, and the atmosphere changes character immediately and completely. The turbulence that rattles aircraft cabins and spills drinks and makes nervous flyers grip their armrests disappears. Weather in any recognizable form ceases to exist. The towering columns of cumulonimbus clouds that punch up from the surface and drive storms simply stop at this boundary. The stratosphere is too stable, too rigidly layered, to allow the vertical convection that creates weather below. The air here moves in slow, horizontal sheets, each layer sitting calmly on top of the one beneath, rarely mixing, rarely disturbing anything. It is the atmospheric equivalent of a library ordered still and somehow more threatening for the silence. From 12 kilometers to roughly 50 kilometers, this is the stratosphere. Temperature behaves here in a way that reverses every intuition built in the troposphere. Instead of cooling with altitude, it warms. The higher the climb through the stratosphere, the warmer the air gets. This seems physically wrong until the reason arrives: ozone. A thin concentration of ozone molecules, each one built from 3 oxygen atoms instead of the usual 2, is scattered through this layer. When ultraviolet radiation from the sun strikes those ozone molecules, the molecules absorb the energy and release it as heat. That process warms the stratosphere from the top down, inverting the temperature gradient that governs everything in the layer below. But the warming is almost incidental. What matters is what that absorption process actually does to the ultraviolet radiation. It stops it. Specifically, ozone absorbs UVC radiation, the shortest, highest energy band of ultraviolet light, the kind that the sun produces in enormous quantities and that would reach the surface in devastating amounts without the ozone layer, intercepting it. UVC does not cause sunburns. It does not darken skin over years of exposure. It directly breaks apart DNA molecules, the double helix that carries the genetic code of every living organism, unzipped and destroyed by direct exposure to UVC. No repair, no adaptation, no sunscreen that addresses it, just molecular dismemberment of the instruction set of life. The ozone layer is the only thing preventing that from happening at the surface of this planet right now. And here is the measurement that should stop everything cold. If all the ozone in the stratosphere were gathered together and compressed to sea level atmospheric pressure, stacked as a pure dense layer, it would be approximately 3 millimeters thick. 3 millimeters. Place 2 credit cards side by side and measure the combined width. That is the ozone layer at sea level pressure. A column of specialized gas thinner than a finger is wide, diffused across a layer of atmosphere stretching from 12 to 50 kilometers altitude, is the only barrier between every living thing on this planet and the radiation that would end biology as it exists on Earth's surface. There is no backup. There is no secondary system. 3 millimeters of ozone spread thin across the upper atmosphere, doing the one job that makes surface life possible, and doing it every second of every day, without any mechanism for self-repair beyond the slow natural chemistry of oxygen and ultraviolet light. In 2023, the Antarctic ozone hole, the seasonal thinning that forms over the South Pole, each southern hemisphere, spring as cold temperatures and certain chemical reactions accelerate. Ozone destruction reached an area of 26 million square kilometers. The measurement comes from the Copernicus Climate Change Service, the European Union's Earth observation program, which tracks ozone levels continuously via satellite. 26 million square kilometers is not an abstraction. It is larger than the entire continent of North America, the United States, Canada, Mexico, all of Central America combined, and still the whole would have room left over. That was the gap in the shield over one region of the planet in a single recent year. Scientists note that the ozone layer has been slowly recovering since the 1987 Montreal Protocol banned the chlorofluorocarbons and other ozone-depleting substances that cause the damage. Recovery, however, is measured in decades. The hole still forms every year. The shield is thinner than it was before industrial chemistry began degrading it, and the return to pre-damage levels is not expected until somewhere in the middle of this century. In October 2012, Felix Baumgartner ascended to 39 kilometers altitude inside a pressurized capsule carried by a helium balloon and then stepped out. The footage from that moment is one of the most visually arresting records of what the stratosphere actually looks like from inside it. Above him, black. Not dark blue, not deep indigo, not the navy of high altitude. Absolute black. The same black as open space, with the sun burning in it as a hard white point of light, rather than the soft, diffuse warmth it appears from the surface. Below him, the curve of Earth unmistakable and sweeping the planet visibly a sphere rather than a flat surface extending to the horizon. He fell for 4 minutes and 20 seconds before his parachute deployed, reaching a peak speed of 843 miles per hour, briefly faster than the speed of sound inside Earth's own atmosphere. While still technically not in space. He was 39 kilometers up. The stratosphere extends to 50. He was still inside it. The U-2 reconnaissance aircraft, developed by Lockheed's Skunk Works division in the mid-1950s, flies operational missions at altitudes between 21 and 25 kilometers firmly inside the terped stratosphere. Its successor, the SR-71 Blackbird, cruised at approximately 24 kilometers at speeds exceeding Mach 3. The pilots of both aircraft wear full pressure suits, the same category of garment worn by astronauts during launch and re-entry. Not as a precaution against unlikely emergencies, as a basic survival requirement. At those altitudes, the atmospheric pressure outside the cockpit has dropped to less than 4% of sea level pressure. The temperature outside the aircraft's skin is around -56 degrees Celsius before accounting for aerodynamic heating. An unprotected human body at 24 kilometers altitude would not simply be uncomfortable. Blood would begin to boil not from heat but from the physics of dissolved gases coming out of solution when external pressure drops below a critical threshold. Loss of consciousness comes within seconds. Death follows quickly. The aircraft is inside Earth's atmosphere. The environment outside it is for a human being already space. Nacreous clouds, also called polar stratospheric clouds or mother-of-pearl clouds, form occasionally in the stratosphere between 15 and 25 kilometers altitude, almost exclusively over the polar regions in winter. They are iridescent, shimmering formations that display colors across the spectrum when lit by sunlight from below the horizon, visible in the pre-dawn or post-sunset window when the surface is already dark. They are genuinely strikingly beautiful. They are also dangerous. Their surfaces of ice crystals and nitric acid particles provide ideal conditions for the chemical reactions that destroy ozone molecules. Even the rare moments of visible beauty in the stratosphere carry a cost measured in molecular destruction of the shield below. The stratosphere asks nothing of the surface and announces nothing of itself. No weather to watch, no colors to see on a clear day, no phenomena that register to unaided human senses at ground level. It is invisible from below, inaudible, unreachable without specialized aircraft or balloons, and it is without question the single most important layer in the atmosphere for the continued existence of life on the surface of this planet. 30 kilometers further up, everything becomes strange in ways that basic physics does not prepare anyone for. 50 kilometers up, the stratosphere is gone. What begins here is colder than anything most people will ever encounter in their lives. Colder than the worst winter on record in Alaska. Colder than the surface of Antarctica during polar night. Colder than the inside of any industrial freezer ever built. The mesosphere, stretching from 50 kilometers to 80 kilometers above the surface, holds the lowest temperatures found anywhere in Earth's atmosphere. At its upper boundary, the air temperature drops to around -90 degrees Celsius. Antarctica, the coldest place on the surface of this planet, recorded its all-time low at -89.2 degrees Celsius at the Soviet Vostok station in 1983. The top of the mesosphere is colder than that. Colder than the coldest recorded point on the entire surface of Earth, sitting quietly above the stratosphere, above the ozone shield, above everything that makes the planet habitable. And almost no one ever thinks about it. The mesosphere does not get the attention of the troposphere with its dramatic weather, or the stratosphere with its ozone layer and its role in protecting life. It sits in the middle of the atmospheric stack, doing something that most people benefit from. Every time they look up at the night sky and see a streak of light, they just do not know the mesosphere is responsible for it. Every shooting star ever seen, every brief bright line traced across a clear dark sky on a summer night, every meteor shower watched from a blanket in a field or a rooftop, all of it happens in the mesosphere. When a piece of rock or metal from space enters Earth's atmosphere, it first encounters the thermosphere above, where the air is so thin that almost nothing happens. But as the object descends into the mesosphere, something changes. The air here is still extraordinarily thin by the standards of the surface, far too thin to breathe, far too thin to support flight, far too thin to transmit sound in any meaningful way. But it is not too thin to matter when an object is traveling at tens of kilometers per second. The process is aerodynamic compression rather than simple friction. As a meteoroid punches downward through the mesosphere, at speeds typically between 11 and 72 kilometers per second, it compresses the air molecules in front of it faster than those molecules can move out of the way. That compression generates heat, enormous, concentrated, almost instantaneous heat. The leading edge of the object reaches temperatures of several thousand degrees Celsius. Rock melts, metal vaporizes. The bright streak visible from the surface is not the meteoroid itself burning in any conventional sense. It is the superheated column of plasma and vaporized material created by that compression event. The object is being destroyed by physics, specifically by the interaction between a fast-moving solid and a gas so thin it barely registers as atmosphere at all. Most of the estimated 40 to 50 metric tons of extraterrestrial material that enters Earth's atmosphere every single day is destroyed in the mesosphere before it ever reaches the surface. The mesosphere is functionally Earth's first line of physical defense against the constant bombardment of space debris, and it performs this defense using air so sparse that a human being inside it would be dead from hypoxia in seconds. And an aircraft inside it would fall from the sky because its wings would generate no meaningful lift. This is the great paradox of the mesosphere. It is simultaneously too thin and too thick. Too thin for aircraft to fly through conventional planes, require a minimum air density to generate the lift that keeps them aloft, and the mesosphere does not provide it. The highest altitude ever reached by an air-breathing aircraft is around 85 kilometers, achieved briefly by experimental rocket-powered craft, not conventional aviation. Standard aircraft are simply physically incapable of reaching this layer. Yet the mesosphere is also too thick for satellites in low Earth orbit. Objects at orbital altitudes need to travel at roughly 7.8 kilometers per second to maintain orbit, and even at 200 kilometers, the lowest practical orbital altitude, the residual atmosphere creates enough drag to gradually slow the spacecraft and cause orbital decay. The mesosphere itself, between 50 and 80 kilometers, would slow an orbiting object so rapidly that maintaining any orbit would be impossible. The mesosphere is therefore a no-man's land in the most literal sense. Aircraft cannot reach it, satellites cannot operate in it. Balloons can enter its lower regions but not its upper reaches. The only vehicles that pass through it are rockets on their way somewhere else, and they pass through it in seconds, not lingering because there is nothing here to linger for. It is the layer of the atmosphere that human technology has the least access to, the least data from, and the least understanding of. Scientists sometimes call it the ignorosphere, not as a joke, but as an acknowledgement that it is the most poorly studied region of Earth's own atmospheric system. What very little does exist here is strange. Noctilucent clouds form between 76 and 85 kilometers, altitude the highest clouds on Earth by a considerable margin, sitting roughly 5 times higher than the highest conventional clouds in the troposphere. They appear only in summer at high latitudes. Only visible during the brief window of twilight, roughly 30 to 60 minutes after sunset or before sunrise, when the sun has dropped below the horizon at the surface, but its light still reaches high enough to illuminate these clouds. From below, while the sky around them is dark, the effect is otherworldly tendrils of electric blue and silver light rippling across a darkened sky, glowing when nothing else does. What makes noctilucent clouds genuinely puzzling is their composition and their behavior. They are made of ice crystals forming around particles, possibly meteoric dust, the remnants of the meteoroids the mesosphere destroys at temperatures that should be too cold for water to exist in any form that could create clouds. And yet they form, and they have been appearing more frequently and at lower latitudes over the past several decades than historical records suggest they should. NASA has referred to them as a phenomenon not yet fully understood. That phrase, not yet fully understood, applied to something happening in Earth's own atmosphere in the 21st century, tells its own story about how much remains unknown, even about the planet directly beneath everyone's feet. Standing in the mesosphere, if such a thing were possible, suited and sealed against the cold and the pressure and the absence of breathable air, the view would be unlike anything experienced from the surface, or even from a commercial aircraft. Above black, the absolute black of space with stars visible in full daylight, because there is no longer enough atmosphere above to scatter sunlight into a sky color. Below the planet, blue and white and curved, unmistakably a sphere. The continents visible as shapes rather than landscapes. The weather systems of the troposphere visible as swirls and patterns below the whole apparatus of the living Earth, spread out underneath like a diagram. What would that feel like? Darkness above, life below, nothing around, suspended in the coldest layer of the atmosphere, in a place no aircraft can reach and no satellite can orbit. If you could stand there for a moment, sky black above Earth glowing below, what does that remind you of from ordinary life? A late-night highway overpass with the city lights below and nothing above, the moment before, a dive into dark, water, something else, entirely. It is worth sitting with that question, because the mesosphere is the last layer where above still feels like above, in any familiar sense. But this is only 80 kilometers, and just above here is what the sun is using to attack Earth continuously, and the only thing stopping it is not matter at all, but magnetic field. At 80 kilometers, the mesosphere ends and something begins that defies the most basic assumptions about what atmosphere means. The thermosphere extends from 80 kilometers to approximately 600 kilometers above the surface. Temperature in this layer climbs to extremes that seem impossible during periods of high solar activity. The thermosphere regularly reaches temperatures of 2000 degrees Celsius, and during the most intense solar events, temperatures can push even higher. 2000 degrees is hotter than the melting point of most metals. It is hotter than lava. It is hot enough that the number itself seems like it belongs to a star's surface, rather than to the atmosphere of a planet that humans live on. And yet a person transported into the thermosphere without any protective equipment would not feel that heat. They would freeze. This is not a contradiction. It is a consequence of density, or rather the near total absence of it. Temperature in the conventional sense of something felt against skin requires molecules colliding with the body and transferring kinetic energy. In the thermosphere, the air is so extraordinarily thin that those collisions happen almost never. There are simply not enough molecules per cubic centimeter to transfer any meaningful thermal energy to a physical object. The individual molecules that exist here are moving at speeds that correspond to 2000 degrees Celsius, but there are so few of them that they carry almost no total heat energy. A thermometer placed in the thermosphere would read temperatures that depend almost entirely on whether it is in sunlight or shadow and how it is measuring, and a suited astronaut standing in the shadow of a large structure in the thermosphere would die of cold long before anything else claimed them. The International Space Station orbits at an altitude of approximately 400 kilometers right in the middle of the thermosphere. This is not a coincidence or an oversight. 400 kilometers is low enough that the station remains within the gravitational embrace of Earth without requiring enormous amounts of fuel to maintain, and it is high enough to orbit without the drag of denser atmospheric layers, pulling it down too quickly. But the environment at 400 kilometers is the thermosphere, which means the station exists in an atmosphere measuring 2000 degrees, while its systems must be designed to handle the extreme cold of shadow, where temperatures drop to around -150 degrees Celsius. On the unlit side, astronauts conducting spacewalks outside the station face both extremes within the same orbit. In direct sunlight, the surface of their spacesuit reaches temperatures around 120 degrees Celsius. Minutes later, passing into Earth's shadow, the same surface drops to -150. The suit must manage a temperature swing of 270 degrees in less time than it takes to watch a short film. This is what working in the thermosphere actually requires. Overlapping the thermosphere through most of its depth is the ionosphere, not a separate layer in altitude terms, but a separate phenomenon driven by the same energy source, the sunday. Ultraviolet and X-ray radiation from the sun is energetic enough at these altitudes to strip electrons from atoms entirely. The process is called ionization, and it transforms what would otherwise be neutral gas molecules into a plasma of charged particles, free electrons, and positively charged ions, coexisting in a layer of electrically active gas that behaves in ways neutral atmosphere does. Not. That electrically active layer is what makes AM radio work the way it does. Radio waves transmitted from the surface travel upward and strike the ionosphere, where the free electrons reflect them back down. At night, when the sun's radiation is no longer maintaining ionization on the side of the Earth facing away from it, the ionosphere shifts and changes, and AM radio signals can skip off it across thousands of kilometers, which is why a clear night AM radio receiver in Ohio can pick up stations from Texas or Mexico with no difficulty, while the same stations are inaudible during the day. The ionosphere is reflecting those signals across the continent using physics that requires a layer of plasma sitting between 80 and 1,000 kilometers above the surface. No ionosphere, no transcontinental AM radio. It is a communication technology dependent entirely on a phenomenon happening in the upper atmosphere. The same solar wind responsible for ionization is also responsible for the most visually spectacular phenomenon that occurs in Earth's atmosphere. When the solar wind, the continuous stream of charged particles flowing outward from the Sun at speeds between 400 and 800 kilometers per second encounters Earth's magnetic field. The field deflects most of it. But at the polar regions, where the magnetic field lines converge and dip toward the surface, some of those charged particles are funneled downward into the upper atmosphere. They collide with oxygen and nitrogen atoms in the thermosphere, transferring energy that the atoms then release as light. The result is the aurora borealis in the northern hemisphere and the aurora australis in the southern hemisphere, curtains and ribbons and shifting veils of green, red and purple light that ripple across the polar skies, visible from the surface on clear nights at high latitudes. Green aurora comes from oxygen at altitudes around 100 kilometers. Red comes from oxygen at higher altitudes above 200 kilometers. Blue and purple come from nitrogen. The colors are a direct read of the atmospheric chemistry at the altitude where the collisions are occurring, a natural spectroscope written across the sky in light. The aurora is not decoration. It is a real-time display of the sun attacking the planet and the planet's magnetic field redirecting that attack into art. There is something both magnificent and deeply unsettling about knowing that Earth is absorbing a continuous assault from its own star, that the solar wind is hitting this planet right now, at this moment, at several hundred kilometers per second, every day, every hour, without pause, and that the shield holding it back is not rock or water or anything physical at all, but an invisible magnetic field generated by the movement of molten iron in a core 3,000 kilometers below the surface. The planet has been running this defense successfully for 4.5 billion years. The aurora is simply the visible proof of how hard it is working. At 600 kilometers, the atmosphere officially disappears, and what begins there is not the empty nothing most people imagine. 600 kilometers. The thermosphere ends here, and what replaces it is almost nothing. Almost, but not quite. The exosphere begins where the thermosphere stops and extends outward to roughly 10,000 kilometers above the surface. That range alone, 10,000 kilometers, is already a number that dwarfs everything encountered in the layers below. The entire troposphere, stratosphere, mesosphere and thermosphere combined span roughly 600 kilometers. The exosphere is more than 15 times that depth, and through all of it the defining characteristic is the same. The air is so thin, it barely qualifies as air at all. In the troposphere, air molecules collide billions of times per second. In the stratosphere and mesosphere, collisions are less frequent, but still constant enough that the gas behaves as a coherent fluid. It flows, it carries heat, it transmits pressure. In the thermosphere, molecular collisions become rare enough that the gas starts behaving less like a fluid and more like a collection of individual particles. In the exosphere, that process reaches its logical extreme. Individual atoms and molecules, mostly hydrogen and helium, the lightest elements, which have not had enough gravitational pull to keep them from drifting this high, travel hundreds of kilometers between collisions, not meters, not kilometers in the conventional sense of a short distance, hundreds of kilometers of unobstructed travel before one particle happens to encounter another. At that density, the concept of atmosphere becomes almost philosophical. Is it still air if the molecules comprising it never interact? Is it still atmosphere if its particles behave identically to particles in interplanetary space? The exosphere is the boundary region where Earth's atmosphere dissolves into. The solar wind not at a sharp line, but through a gradient, so gradual that the transition from planetary atmosphere to interplanetary space is a matter of definition rather than physics. That question of definition leads directly to the Kármán line, 100 kilometers altitude, the boundary that the Fédération Aéronautique Internationale, the international body that certifies aviation and astronautical records, designates as the official edge of space. The reasoning behind that specific number is aerodynamic rather than arbitrary. At 100 kilometers altitude, the atmosphere has thinned to the point where a vehicle moving fast enough to generate aerodynamic lift, the kind of lift that keeps aircraft flying, would need to be traveling at orbital velocity to do so. Orbital velocity for Earth is approximately 7.8 kilometers per second. Any slower, the vehicle falls. Any faster, it is no longer flying in any aerodynamic sense, it is orbiting. which is an entirely different physical regime governed by gravitational mechanics rather than the interaction between wings and air molecules. Below the Kármán line, flight is possible. Above it, only orbit exists. The line marks the altitude where aerodynamics stops and orbital mechanics begins, where being an aircraft ends and being a spacecraft starts. It is a definition rooted in physics, which is why it is held up as the standard, even as debates about its exact placement continue among scientists who prefer slightly different altitudes based on different measurement criteria. The exosphere then begins well above even that boundary. By the time the altitude reaches 600 kilometers and the exosphere properly begins, the Kármán line is already 500 kilometers below. The question of whether something is in space or not has long been answered. Everything in the exosphere is unambiguously in space, just space that still carries a faint fingerprint of Earth's influence. That influence stretches further than most people realize. The Moon's gravity is strong enough to interact with the outermost reaches of Earth's exosphere, the geocorona, a cloud of hydrogen atoms extending from the exosphere outward. In 2019, scientists analyzing data from the solar and heliospheric observatory satellite data that had been collected in 1999 but reanalyzed decades later determined that the geocorona extends as far as 630,000 kilometers from Earth. The Moon orbits at an average distance of 384,000 kilometers. This means the Moon is inside Earth's atmosphere. Not in a meaningful physical sense, the density at that distance is so infinitesimally small that it exerts essentially no measurable effect on the Moon's surface or motion. But technically, geometrically, the outermost wisps of Earth's atmosphere extend past the Moon's orbit. The two bodies are in the most technical sense possible, touching, connected by a gossamer thread of hydrogen atoms too sparse to detect without purpose-built instruments. Earth and the Moon are not separated by empty space. They are connected by atmosphere so thin it took decades to notice. What is not thin and not subtle and not easy to miss once the numbers are laid out plainly is what humanity has placed in the region between the Kármán line and the exosphere in the 70 years since Sputnik made the first orbit in 1960. The United States Space Surveillance Network, operated by the Department of Defense, currently tracks approximately 27,000 individual pieces of debris in orbit around Earth. These are objects large enough, generally 10 centimeters or larger, for ground-based radar and optical systems to detect and follow. Every one of them has a catalogued orbit, a size estimate, and a predicted trajectory updated continuously as atmospheric drag and gravitational interactions shift their paths. 27,000 tracked objects. The actual number of objects in orbit is orders of magnitude higher. Estimates from NASA and the European Space Agency place the number of debris pieces between 1 and 10 centimeters at around 500,000. Objects smaller than 1 centimeter fragments from collisions, flecks of paint, solidified droplets of coolant from old Soviet-era nuclear-powered satellites number in the tens of millions. None of those can be tracked. They travel at orbital velocities between 7 and 8 kilometers per second. At that speed, a 1 centimeter fragment carries kinetic energy comparable to a safe dropped from a building. A collision with an active spacecraft at that velocity does not produce a dent. It produces a cloud of new fragments, each of which becomes its own debris hazard, each capable of generating more fragments in subsequent collisions. This cascade failure scenario has a name, the Kessler syndrome, proposed by NASA scientist Donald Kessler in 1978, and it describes a threshold beyond which the density of orbital debris becomes self-sustaining, generating new collisions faster than debris naturally deorbits. Some researchers believe certain orbital shells around Earth are already approaching that threshold in specific altitude bands. Humanity reached space in 1957. In the approximately 7 decades since the crowning collective achievement in that environment, the thing that distinguishes low Earth orbit from every other region of space encountered on this journey is that it has been converted into the largest debris field in the solar system. Every other planet, every moon, every region of interplanetary space is cleaner than the shell of altitude sitting directly above Earth's atmosphere. The one place in the cosmos where human activity has been most concentrated is the one place most thoroughly filled with wreckage. It is in the most deadpan possible reading of the situation an impressive accomplishment. The exosphere eventually fades, the geocorona thins to nothing. The last hydrogen atoms drift too far from Earth to count as atmosphere in any meaningful frame. What was a planet with layers and boundaries and definable edges becomes simply a gravitational source in open space, a mass with an orbital influence but no physical envelope left to speak of. The handoff is not dramatic. There is no line where Earth definitively ends. Only a continuing diminishment of presence until presence is indistinguishable from absence. And then the journey continues outward into the territory of the solar system proper, where the distances dwarf everything encountered so far by a factor that makes the entire atmosphere from the ground to the exosphere's edge look like a single step on a walk measured in continents. Beyond the exosphere, the vertical journey enters the territory of the solar system, and the first number encountered will make everything before it look like a child's first step. 384,400 kilometers. That is the average distance between Earth and the Moon. Not the distance to Mars, not the distance to the outer planets, not some abstract measurement pulled from the deep solar system. The distance to the nearest object in space that humans have ever physically visited. 384,400 kilometers. And most people, when they look up at the Moon on a clear night and see it hanging there, looking close enough to touch, have no working intuition for what that number actually means in physical space. Here is one way to feel it. Take every planet in the solar system other than Earth, Mercury, Venus, Mars, Jupiter, Saturn, Uranus, Neptune, line them up side by side, diameter touching diameter, and measure the total width of that lineup. The combined diameter of all 7 planets fits inside the Earth-Moon distance with room to spare. Jupiter alone is 140,000 kilometers across. Saturn is 116,000 kilometers wide. Stack all 7 planets in a row, and the total comes to just under 380,000 kilometers. The gap between Earth and the Moon is wider than that entire planetary parade. Every world in the solar system, other than the one beneath our feet, could be arranged in the space between here and the Moon, and there would still be kilometers of empty room on either end. That gap is not empty. That is the first thing to understand, and the most consistently underestimated fact about the Earth-Moon transit. The space between the two bodies is threaded continuously with solar wind, the stream of charged particles flowing outward from the Sun at between 400 and 800 kilometers per second. It carries cosmic radiation from sources far outside the solar system. High-energy particles generated by distant supernova explosions that travel for thousands of years before arriving here. It contains interplanetary dust, microscopic particles of rock and debris that fill the inner solar system in a diffuse haze invisible to the naked eye, but measurable by sensitive instruments. And critically, unlike everything encountered in the lower atmosphere, none of it is blocked by anything meaningful. No ozone layer. No magnetic field strong enough to deflect particles at these distances from Earth's core. The transit between Earth and the Moon is an unshielded crossing of genuinely hostile space. The Apollo astronauts made that crossing protected by aluminum hull panels a few millimeters thick. That is not a metaphor for thin protection. It is the literal specification of the command module hull that carried 12 human beings to the Moon and back between 1969 and 1972, several millimeters of aluminum alloy between the crew and the radiation environment of cislunar space. The engineering calculation was not that the hull would stop radiation, it cannot. Aluminum is relatively poor at blocking high-energy particles, but that the transit time was short enough that the accumulated dose would not be immediately lethal. A calculated gamble with the lives of the people inside, made on the basis that speed through the zone was the best available mitigation. The effects were measurable and strange. Multiple Apollo astronauts reported seeing flashes of light with their eyes closed. Not hallucinations, not artifacts of fatigue, but actual visual stimulation caused by cosmic ray particles passing directly through the eyelid and striking the retina without the light entering the eye at all. The particles were energetic enough to pass through bone and tissue and interact with the photoreceptors in the back of the eye, producing a signal the visual cortex interpreted as light because that is the only signal it knows how to interpret from that pathway. The astronauts were seeing cosmic rays, with their eyes shut, in the dark interior of the spacecraft. Buzz Aldrin reported the phenomenon. So did other crew members on subsequent missions. It became a known feature of deep space transit, the body registering in the only way it could, the radiation passing through it constantly. The navigation reality of that distance adds another dimension that the number alone does not convey. Light travels at approximately 300,000 kilometers per second. The Earth-Moon distance of 384,000 kilometers means that light, and therefore any radio signal, any command, any communication, takes 1.3 seconds to cross it, one way. A round trip for any signal takes 2.6 seconds minimum. That delay is not a technical inconvenience. It is a fundamental physical constraint that shaped one of the most consequential decisions in the history of spaceflight. During the final 13 seconds of Apollo 11's descent to the lunar surface on the 20th of July, 1969, Neil Armstrong took manual control of the Eagle lander because the onboard computer was steering the spacecraft toward a boulder-strewn crater unsuitable for landing. The decision to override the search for a safer site, the manual piloting to the flat ground of the Sea of Tranquility, all of it happened in 13 seconds. Mission Control in Houston was watching telemetry and could hear the communication but could not intervene. Any command sent from Earth would take 1.3 seconds to arrive, by which time the situation would have already resolved, one way or another. Armstrong was alone with the decision in a way that had nothing to do with courage and everything to do with the physics of distance. The moon was too far away for anyone else to help in real time. That is 384,000 kilometers. That is what the nearest object in space actually means when a human being is trying to land on it. But the moon is only the first stop, and above it exists something that 500 years ago no one knew. Was there something that right now is directly affecting every piece of modern technology orbiting this planet? They were discovered by accident. In 1958, the United States launched Explorer 1, its first successful satellite carrying a Geiger counter, designed by physicist James Van Allen of the University of Iowa. The instrument was meant to measure cosmic radiation in low Earth orbit. Instead, at certain altitudes, it stopped returning readings entirely. The first interpretation was equipment failure. The correct interpretation, which Van Allen arrived at after analyzing the data more carefully, was that the radiation was so intense it had saturated the detector, overwhelmed its ability to count individual particles, because the particles were arriving faster than the instrument could register them. There was so much radiation that the instrument measuring it gave up. What Van Allen had found were two massive donut-shaped regions of space encircling Earth, held in place by the planet's magnetic field, packed with charged particles, electrons, and protons, trapped in spiraling paths along magnetic field lines bouncing back and forth between the polar regions. At speeds approaching the speed of light, the inner belt extends from roughly 1,000 to 12,000 kilometers above the surface. The outer belt runs from approximately 13,000 to 60,000 kilometers. Between them is a relatively calmer gap, and beyond the outer belt open space. But both belts represent radiation environments of a severity that has shaped every human spaceflight decision made since their discovery. The inner belt is the more intensely dangerous of the two. Proton flux in the inner Van Allen belt. The density of high-energy protons passing through a given area per second is high enough that an unprotected human being inside it would receive a lethal radiation dose within hours. Not days, hours. The particles penetrate tissue, disrupt cellular chemistry, break DNA strands in ways that cause acute radiation syndrome, nausea, hair loss, immune system failure, organ damage, death. No amount of physical toughness or medical intervention changes the underlying physics. The radiation is there, the body absorbs it, and past a certain accumulated dose, the outcome is determined. Spacecraft transiting the Van Allen belts must either move through them quickly. The Apollo missions were designed to pass through the belts on a trajectory that minimized transit time and cumulative dose, or carry radiation shielding, specifically designed to reduce the particle flux reaching sensitive electronics and crew. The Apollo command modules passed through the belts in roughly 30 minutes on the way out and 30 minutes on the return, keeping total crew radiation exposure to levels judged acceptable for the mission duration. Acceptable, not safe. Every Apollo astronaut received a radiation dose during the transit. The calculation was that the mission objectives justified the exposure. The Parker Solar Probe, launched by NASA in 2018 to study the Sun's corona and solar wind at closer range than any previous spacecraft had. Its entire orbital trajectory, designed partly around avoiding the most dangerous portions of the Van Allen belts during its early mission phases. A spacecraft built to withstand the radiation environment near the Sun still required careful routing to manage its exposure to the radiation environment surrounding Earth. That fact alone communicates something about the intensity of what is trapped in those belts. The South Atlantic anomaly is where the Van Allen belts become a problem not for deep space missions, but for spacecraft in low Earth orbit, including the International Space Station. The anomaly exists because Earth's magnetic field is not a perfect symmetrical dipole centered on the planet's core. It is offset slightly and tilted. And as a result, the inner Van Allen belt dips closer to the surface over the South Atlantic Ocean than anywhere else on the planet, coming as low as 200 kilometers above the surface. In some models, which overlaps directly with the orbital altitude of most low Earth orbit satellites and the station itself. When the International Space Station passes over the South Atlantic anomaly, which it does multiple times per day given its orbital period of approximately 90 minutes, the crew receives a measurably higher radiation dose than during any other portion of the orbit. More consequentially, the computers and electronics aboard the station experience increased error rates. Single event upsets, bit flips in memory caused by a charged particle striking a transistor and temporarily or permanently flipping its state from 0 to 1 or 1 to 0 happen more frequently over the anomaly than anywhere else in the orbit. The station's computers are designed with redundancy and error correction specifically to handle this, because the alternative is a critical system making a decision based on corrupted data while orbiting at 7.8 kilometers per second. The South Atlantic anomaly is also growing. Satellite data compiled over decades shows the region is expanding westward, and the field intensity in the area is continuing to weaken. Earth's magnetic field globally has lost roughly 9% of its average intensity over the past 170 years, a rate of change that geophysicists consider significant. Though whether it represents the beginning of a geomagnetic reversal or simply a fluctuation in the ongoing dynamics of the liquid outer core remains an open question. Earth's magnetic field has reversed before north becoming south, south becoming north, with the reversal process taking thousands of years, and the field weakening substantially during the transition. The geologic record shows it has happened hundreds of times in the planet's history. It will happen again. The question is not whether, but when, and what the consequences would be for satellite technology, power grids, and human health during the prolonged period of weakened magnetic protection. If Earth's magnetic field began weakening significantly, and it is doing so slowly right now, which generation do you think would be the first to feel the consequences? Clearly, not as statistics in a scientific paper, but as lived reality. Satellites failing more often, power grids more vulnerable, to solar storms, radiation exposure increasing at high altitudes, the aurora visible from latitudes that have never seen it before. The answer is not obvious. And it depends on how fast the process accelerates, but the process is already underway. Leaving the Van Allen belts, the journey moves into space that human probes have taken decades to cross, and the first distance encountered there will make everything before it collapses into irrelevance on any meaningful scale. The vertical journey has a problem that nobody mentions in school. Directly above is not a fixed address. Earth rotates once every 24 hours, which means a point on the surface in the middle of the United States, say somewhere in Kansas, is sweeping through space at roughly 1,600 kilometers per hour relative to Earth's axis. At the same time, Earth is orbiting the Sun at approximately 107,000 kilometers per hour. The Sun is moving through the galaxy. The galaxy itself is moving. Stack all those motions together, and the direction straight up from any fixed point on the surface traces a continuously shifting line through the solar system, pointing at a completely different region of interplanetary space from 1 hour to the next, 1 day to the next, 1 season to the next. In January, the vertical line from a location in Texas at noon points in a direction that extended outward passes through a particular region of the inner solar system. 6 months later, the same location at the same local time points in essentially the opposite direction, because Earth has traveled halfway around its orbit. The question of what sits directly above any specific point is not just complicated, it is a question whose answer never stops changing, requiring continuous recalculation against the orbital mechanics of every body in the system. With that understood, the distances involved can be confronted honestly. Planetary distances are measured in astronomical units, one astronomical unit being the average distance from Earth to the Sun, approximately 150 million kilometers. It is a useful unit because the numbers in kilometers become unwieldy almost immediately when dealing with anything beyond the Moon. Mars, the planet most discussed as a destination for human spaceflight, ranges between 0.5 and 2.5 astronomical units from Earth, depending on where both planets sit in their respective orbits. At closest approach, a configuration called opposition when Earth passes between Mars and the Sun, Mars can be as close as 54 million kilometers. At its farthest, when both planets are on opposite sides of the Sun, the distance stretches to over 400 million kilometers. The same planet, the same solar system, a range of distances spanning a factor of nearly 8, depending entirely on orbital timing. Jupiter sits between 4.2 and 6.2 astronomical units from Earth. That translates to a minimum distance of roughly 600 million kilometers at closest approach. Light traveling at 300,000 kilometers per second takes between 32 and 52 minutes to cover that distance, which means any photograph taken of Jupiter shows the planet as it existed between half an hour and nearly an hour ago, not as it is now, as it was. Looking at Jupiter is looking into the past even within the same solar system. Saturn is more distant still, between 8.2 and 11.2 astronomical units depending on orbital positions. Light from Saturn takes between 70 and 90 minutes to reach Earth. When the Cassini spacecraft was orbiting Saturn and mission controllers in Pasadena needed to send a command, they transmitted it, knowing the signal would take over an hour to arrive. When Cassini executed the command and sent back confirmation, that signal took another hour to return. A 2-hour round trip for a single instruction within the solar system that contains Earth using signals traveling at the speed of light. Voyager 1 has been traveling since September 1977. It launched on a trajectory designed to use gravitational assists from Jupiter and Saturn to slingshot outward at velocities no rocket alone could achieve. In 35 years of continuous travel, by 2012, Voyager 1 had covered approximately 23 billion kilometers and was still inside the solar system by the definition of the heliosphere, the bubble of solar magnetic influence that extends outward from the Sun in all direction. Humanity's farthest traveling spacecraft, carrying the accumulated engineering achievement of the 1970s space program, moving for 3.5 decades without stopping, and still not yet out of the solar system. 23 billion kilometers in 35 years, and still inside. There is a particular irony in the search for liquid water, the baseline requirement for life as understood from the only example available that approaches something almost poetic. The nearest world beyond Earth where liquid water is considered likely to exist is Europa, the 4th largest moon of Jupiter. Europa's surface is a shell of water ice cracked and reworked by tidal forces from Jupiter's immense gravity into a landscape of fractured plates and refrozen ridges. Beneath that ice, models strongly supported by data from the Galileo spacecraft and subsequent analysis suggest a liquid water ocean containing more water than all of Earth's oceans combined, kept liquid by tidal heating. From Jupiter's gravitational pull, the conditions for life by every metric used to evaluate habitability exist more plausibly in that subsurface ocean than on the surface of Mars. Europa is between 600 million and 900 million kilometers away. The closest any human being has ever physically traveled from Earth is the Moon, 384,000 kilometers. The world most likely to harbor liquid water beyond Earth is 2,000 times farther away than the farthest point any human has reached. There is something in that ratio, 2,000 times beyond the limit of human exploration, holding an ocean that may or may not be empty, that resists easy framing. It is not discouraging exactly. It is simply the scale of the problem, stated honestly. But the real boundary of the solar system is not Saturn, and it is not even Neptune. It is something enormous, strange, and almost entirely unexplored. The Sun does not end at its visible surface. That surface, the photosphere, the layer from which light escapes and travels outward to illuminate planets, is where most people mentally locate the boundary of the Sunday. But the Sun's influence extends far beyond that in the form of the solar wind, the continuous outflow of charged particles, electrons and protons, and heavier ions streaming outward in all directions at speeds between 400 and 800 kilometers per second. This wind does not stop at any planet's orbit. It does not weaken to nothing at the asteroid belt or at Jupiter's magnetosphere. It continues outward, thinning gradually for an enormous distance until it finally collides with the interstellar medium, the material filling the space between stars, and can push no further. The region enclosed by that boundary is the heliosphere. It is an asymmetric bubble compressed on the side facing the direction of the Sun's motion, through the galaxy stretched into a long tail on the opposite side, extending roughly 100 astronomical units from the Sun in the direction it faces, and considerably farther in the trailing direction. 100 astronomical units is 15 billion kilometers. The heliosphere is the Sun's domain, and everything within it, every planet, every moon, every asteroid, every comet in its inner orbit exists under the Sun's magnetic protection, partially shielded from the cosmic rays and interstellar particles that fill the space between stars. Voyager 1 crossed the heliopause, the boundary where the solar wind pressure equals the pressure of the interstellar medium, and the Sun's bubble effectively ends in August 2012. Scientists confirmed the crossing by analyzing the plasma density data the probe was returning, which shifted sharply to match the denser interstellar medium outside. It was the first human-made object to enter interstellar space. Voyager 1 left Earth in 1977. It took 35 years of continuous travel at speeds exceeding 60,000 kilometers per hour to reach the edge of the Sun's influence, 35 years to exit the solar neighborhood. Beyond the heliopause lies the interstellar medium proper, a different environment entirely. The solar wind no longer reaches it. The Sun's magnetic field no longer shapes it. Instead, the space between stars carries its own magnetic field, its own particle flux radiation from other stellar sources, the accumulated debris of supernovae and stellar winds from hundreds of thousands of other star systems. It is not empty. It is simply no longer home. Inside the heliosphere, between the planetary orbits of the inner solar system and the heliopause, at 100 astronomical units, there is a region of space that has its own name and its own geometry, and it dwarfs everything encountered, so far by a factor that requires a moment of stillness to absorb. The Oort cloud occupies a spherical shell, estimated to begin at around 2,000 astronomical units from the Sun, and extend to approximately 100,000 astronomical units. 2,000 to 100,000. The inner edge is 20 times farther from the Sun than the heliopause. The outer edge is 1,000 times farther. The Oort cloud is the origin point of long-period comets, the objects that arrive in the inner solar system on orbital periods of thousands or millions of years, traveling from the outermost reaches of solar gravitational influence on trajectories so elongated they barely qualify as ellipses. When a comet appears from an unexpected direction with a period measured in millennia, it has almost certainly come from the Oort cloud. Disturbed from a stable orbit by the gravitational nudge of a passing star, or the tidal pull of the galactic disk beginning a journey inward that takes thousands of years to complete. The number of objects in the Oort cloud is estimated in the trillions. Trillions of icy bodies, water ice, frozen methane, frozen carbon dioxide mixed with rock and dust orbiting in the outermost gravitational embrace of the Sun, at distances so vast that the Sun itself seen from the Oort cloud's inner edge would be an extremely bright star rather than a disk. From the outer Oort cloud, the Sun would be indistinguishable to the naked eye from thousands of other stars in the sky. And there are potentially more objects in the Oort cloud than there are stars in the entire Milky Way galaxy. Trillions of icy bodies compared to the galaxy's estimated 200 to 400 billion stars. The solar system's most numerous population lives in its most distant, most invisible region. Voyager 1, which crossed the heliopause in 2012 and is currently the most distant human-made object ever built, will not reach the inner edge of the Oort cloud for approximately 300 years. At its current speed of about 17 kilometers per second, the probe that represents humanity's greatest reach into space will spend 3 centuries crossing the gap between the heliopause and the first objects of the Oort cloud, and then would need thousands of years more to cross the cloud itself. No spacecraft currently being planned or designed will reach the Oort cloud within any time frame that current civilization would recognize as near-term. The Oort cloud was proposed by Dutch astronomer Jan Oort in 1950, based on the orbital characteristics of long-period comets. Astronomers have used it to explain comet origins for over 80 years. It appears in every astronomy textbook, every introductory course on the solar system, every diagram of the sun's domain, and not one human-built instrument has ever directly observed a single object within it. Every piece of evidence for its existence is indirect inferred from the behavior of comets, from gravitational modeling, from theoretical predictions about how the outer solar system formed. The Oort cloud is, in the most precise scientific sense, a region humanity has named, mapped, in theory, studied in consequence, and never once actually seen. It is the scientific definition of taking something on faith, not religious faith, but the rigorous evidence-backed, mathematically consistent faith that physicists extend to things whose existence is demanded by everything else that is known to be true. Beyond the sun's influence, the vertical journey enters the true territory of the Milky Way, and the next layer of mystery changes everything understood about what distance actually means. The Oort cloud fades. The last gravitational whisper of the sun dissolves into background noise, and the journey enters something that has no adequate name in any human language, because no human sensory experience, no landscape, no environment ever encountered on Earth or in low orbit comes anywhere close to preparing the mind for what interstellar space actually is. The nearest star to the sun is Proxima Centauri, a small red dwarf gravitationally bound to the Alpha Centauri system, sitting at a distance of 4.24 light-years. A light-year is the distance light travels in 1 year, moving at approximately 300,000 kilometers per second without stopping, without slowing, for the full 365 days. 4.24 light-years translates to roughly 40 trillion kilometers, written as a numeral. 40 followed by 12 zeros. That is the distance to the closest star, not to a distant galaxy, not to some exotic object at the edge of the observable universe, to the nearest neighbor, the one right next door by astronomical standards. Voyager 1, currently the fastest and farthest human-made object ever launched, is traveling at approximately 17 kilometers per second, a speed achieved through gravitational assists from Jupiter and Saturn that no rocket, currently in existence, could replicate from a standing start. At that speed, covering the 40 trillion kilometers to Proxima Centauri would take approximately 73,000 years, not 73,000 days, not 73,000 months. 73,000 years. Modern human civilization, agriculture, writing, cities, recorded history is roughly 10,000 years old. The journey to the nearest star at the fastest speed humanity has ever propelled an object would take more than 7 times the entire span of recorded human history. Voyager 1 was launched in 1977. It is not heading toward Proxima Centauri. Its trajectory points in a different direction entirely, but the comparison holds regardless. In the time since the American Revolution, Voyager has covered about 23 billion kilometers. Proxima Centauri is 40 trillion kilometers away. The math is not encouraging. The space between those 2 points, between the outer boundary of the solar system's influence and the beginning of Proxima Centauri's own gravitational domain, is the interstellar medium, and the most important thing to understand about it is this: it is not empty. Empty implies an absence of content, a void, a null space. The interstellar medium has content. It contains hydrogen atoms, helium atoms, trace amounts of heavier elements, molecular clouds in some regions, dust, grains of carbon, and silicates, magnetic fields threading through it, cosmic rays, photons from every star in the galaxy, passing through in every direction simultaneously. It is not a vacuum in the engineering sense of the word. What it is incomprehensibly sparse. The average density of the interstellar medium is approximately 1 atom of hydrogen per cubic centimeter. 1 atom. A single hydrogen atom, the simplest element in the periodic table, 1 proton and 1 electron, occupying a volume the size of a sugar cube. Compare that to the air being breathed right now at sea level. 1 cubic centimeter of ordinary air contains approximately 27 million trillion molecules, 2.7 times 10 to the 19th power. That number is so far beyond intuitive grasp that comparisons break down almost immediately, but the attempt is worth making. If the interstellar medium were a crowd and each atom were a person filling a cubic centimeter, with interstellar medium density would mean one person standing alone in a space the size of a sugar cube. Filling the same volume with sea level air density would require stacking 27 million trillion people into that same sugar cube. The difference between breathing air and interstellar space is not a difference of degree. It is a difference of kind, a chasm between two states of matter so extreme they barely belong in the same conversation. The best vacuum achievable in a laboratory on Earth, produced by sophisticated pumping equipment, carefully sealed chambers and significant engineering effort, is still orders of magnitude denser than the interstellar medium. The most perfect vacuum humans have ever manufactured is crowded compared to the space between stars. Interstellar space is not something that can be replicated. It is the natural state of most of the universe's volume, and it is more empty than anything human technology can produce. Temperature in this environment sits at 2.7 Kelvin, negative 270.45 degrees Celsius. This is not a temperature produced by any local cooling process. It is the cosmic microwave background radiation, the relic heat of the Big Bang itself, the afterglow of the universe's formation, 13.8 billion years ago, now redshifted and cooled by the expansion of space to a nearly uniform bath of microwave radiation permeating every point in the observable universe. 2.7 Kelvin is as close to absolute zero, the theoretical lower limit of temperature, where all thermal motion ceases as the universe gets in the regions between stars. Absolute zero is 0 Kelvin. Interstellar space sits less than 3 degrees above it. This is the ambient temperature of most of the universe, not the temperature near a star, not near a black hole, not in some exotic environment, just the ordinary background state of space between stellar systems. The universe in its default condition is 3 degrees above the coldest anything can possibly be. Now consider the second nearest star system. Alpha Centauri A and Alpha Centauri B are a binary pair, 2 stars orbiting each other gravitationally bound, located 4.37 light-years from the Sun. They are slightly farther than Proxima Centauri, which is itself a third member of the same system orbiting the binary pair at a considerable distance. Alpha Centauri A is similar in size and type to the Sun, a yellow dwarf star slightly larger and brighter. Alpha Centauri B is slightly smaller and dimmer, an orange dwarf. They orbit each other with a period of about 79.9 years, separated by a distance that varies between 11 and 36 astronomical units, depending on where they are in their mutual orbit. The scale model makes this real in a way raw numbers cannot. If the Sun were reduced to the size of a standard basketball, roughly 24 centimeters in diameter, then on that same scale, Alpha Centauri A and B would be located approximately 4,500 kilometers away. A basketball sitting somewhere in the middle of the United States and its nearest stellar neighbors sitting 4,500 kilometers across the ocean. The two objects, each the size of a basketball or slightly smaller, separated by 4,500 kilometers of space, containing essentially nothing. That is the density of stellar population in the Milky Way's neighborhood. 2 basketballs, 4,500 kilometers apart, and the space between them cold beyond any experience, sparse beyond any laboratory's ability to replicate, silent in every wavelength a human ear could detect. The Milky Way contains somewhere between 200 billion and 400 billion stars. Those stars are distributed across a disk roughly 100,000 light-years in diameter. The average distance between stars in the galaxy's disk accounting for the denser regions near the center and the sparser regions toward the edges, is measured in light years, not fractions of light years. Individual stellar systems are islands, separated from their neighbors by interstellar distances that dwarf the size of the systems themselves in exactly the way the basketball model illustrates. The galaxy is not a crowded place. It is an ocean of near nothing dotted with occasional sources of light and heat, each one isolated from the others by distances that make the Earth-Moon gap look like a step across a puddle. Standing conceptually in the interstellar medium, if such a thing were possible, the sun behind would be a bright star, the brightest in the sky, but still just a star. Proxima Centauri ahead would be invisible to the naked eye, too dim to see, without optical aid, despite being the nearest stellar object. In every direction, stars would be visible as points of light against the black, beautiful, distant, unreachable, on any timescale that maps onto human experience. And the space surrounding that hypothetical position would be the most perfect quiet in the physical universe. 1 hydrogen atom per cubic centimeter, 2.7 Kelvin. No weather, no sound, no molecular collisions, nothing moving except the cosmic microwave background washing through at the speed of light in every direction simultaneously. This is the galaxy between its stars. This is what most of its volume actually is. Even these enormous distances are only small steps in the structure that comes next, something that even modern astronomy struggles to fully measure. Step back far enough and the solar system disappears. Not metaphorically, literally. Pull the perspective out to the scale of the Milky Way and the Sun, with all its planets and moons and comets, and the entire domain of its gravitational influence becomes a single point of light, indistinguishable from the 200 to 400 billion other points of light scattered across the galaxy's disk. NASA and ESA estimates place the stellar population of the Milky Way somewhere in that range, 200 billion on the conservative end. 400 billion if the census of dim red dwarfs is more complete than current surveys suggest. Either number is beyond genuine comprehension. What matters for orientation is the shape of the structure containing all of them. The Milky Way is a barred spiral galaxy, a flattened disk with a central bar-shaped region of older stars, spiral arms curling outward from the ends of that bar, and a central bulge surrounding a supermassive black hole at the core. The disk spans approximately 100,000 light-years in diameter. Its thickness varies, but through most of the disk it runs roughly 1,000 light-years deep. The geometry is something like an enormous vinyl record thin relative to its width, structured in concentric patterns rotating. Everything in it orbits the center, but not like a rigid body. Different regions orbit at different speeds, the spiral arms themselves representing density waves moving through the stellar population rather than fixed structures of stars rotating in lockstep. The Sun sits in a minor spiral feature called the Orion Spur, sometimes called the Orion Arm or the Local Arm, located between the larger Sagittarius Arm and the Perseus Arm. It is not a prominent position. It is not the center where the oldest stars cluster around the galactic bar and the radiation environment near Sagittarius A times the supermassive black hole at the Milky Way's core. With a mass of approximately 4 million solar masses, would sterilize any planetary surface through X-ray and gamma-ray flux many times more intense than what Earth currently receives. It is not the outer edge either, where stellar density thins to near nothing and the raw material for planet formation grows scarce. The Sun sits approximately 26,000 light-years from the galactic center, roughly halfway out from the core to the disk's edge, in a relatively calm, moderately populated region of the galaxy, where stellar encounters are rare, supernovae are distant enough to be non-lethal, and the conditions for a stable, planetary system persisting for billions of years are about, as favorable as they get anywhere in the Milky Way. Whether that placement is coincidental or represents some selection effect, only systems in stable galactic neighborhoods surviving long enough to develop complex life is a question that remains genuinely open. The Sun is not stationary in that position. It orbits the galactic center at approximately 230 kilometers per second, fast enough that sitting still relative to the galaxy is not an option, yet slow enough that completing one full orbit takes between 225 and 250 million years. Astronomers call this period a galactic year or a cosmic year. Earth has completed approximately 20 of these orbits since its formation, 4.5 billion years ago, 20 trips around the galaxy. The last time Earth was in the same position relative to the galactic center that it occupies today, the dominant life forms on its surface were the earliest dinosaurs. The trip before that, it was before the Permian extinction. Each galactic year contains more geological and biological history than any single narrative can hold. Now consider the direction of this journey straight up perpendicular to Earth's surface. The critical detail is the angle. The Milky Way's disk is not aligned with Earth's equatorial plane or with the ecliptic plane of the solar system. The galactic plane cuts across the sky at an angle, and whether straight up from any given point on Earth's surface is perpendicular to that galactic plane or at some other angle depends on latitude, time of year, and time of day. But if the vertical line of this journey happens to be directed perpendicular to the galactic disk, straight out through the thin dimension of the galaxy, rather than along its length, the geometry produces something remarkable. The disk is 1,000 light-years thick in most regions. The Sun sits somewhere within that thickness. Traveling perpendicular to the disk, the distance to the edge is not 100,000 light-years the diameter. It is a few hundred light-years at most, depending on the Sun's exact vertical position within the disk. After roughly 500 light-years of travel in the right direction, the stars thin rapidly. The disk falls away. And looking back, if looking back were possible, the full structure of the Milky Way would be visible as an external object for the first time. No human instrument has ever taken that photograph. The Milky Way has never been imaged from outside because no spacecraft has traveled anywhere near far enough to achieve that perspective. Every image of a spiral galaxy labeled as similar to the Milky Way is an image of a different galaxy entirely. Andromeda Triangulum, NGC 1232, some other spiral system photographed from a vantage point within the Milky Way itself. What the Milky Way actually looks like from outside in full detail remains something inferred from structure rather than observed directly. If you could stand outside the galactic disk and look back at it, the full spiral structure visible, the bar at the center, the arms curving outward, the thin disk, edge on or face on depending on perspective, and somewhere in that structure, a faint point of light marking the Orion spur, and within that point, invisible at this scale, a single star with a single inhabited planet, what would that do to you? Not philosophically, personally. Would it feel like liberation? Seeing the full picture from outside, would it feel like loss? The home reduced to a coordinate, would it change what the word home means at all? It is worth sitting with that question, because the perspective it describes is real, even if no instrument has yet achieved it. Leaving the Milky Way, the journey confronts a scale that the human brain was simply not built by evolution to process. The Milky Way is not alone. Gravity operates at galactic scales just as it operates between planets and stars, and the result is that galaxies cluster. The Milky Way belongs to a gravitationally bound collection of galaxies called the Local Group, approximately 54 members in current catalogues, though the count shifts as surveys improve and smaller dwarf galaxies are discovered, lurking at the edges of the group's territory. The Local Group spans roughly 10 million light-years in its longest dimension, an irregular volume of space containing everything from the two dominant spirals, the Milky Way and Andromeda, down to dwarf spheroidal galaxies, so faint and sparse they barely register as distinct structures against the intergalactic background. Andromeda, designated M31 in the Messier catalogue, is the largest member of the Local Group and the most massive galaxy in the neighborhood by some estimates. It sits at a distance of approximately 2.537 million light-years. The light currently arriving from it left when the most complex life on Earth was simple multicellular organisms in shallow seas. Andromeda contains roughly 1 trillion stars, making it significantly more populated than the Milky Way's 200 to 400 billion. It is visible to the naked eye from dark locations in the northern hemisphere as a faint smudge in the constellation Andromeda, the most distant object most human eyes will ever detect without optical aid, a trillion-star galaxy reduced to a dim patch by 2.5 million light-years of intervening space. Andromeda is not staying at that distance. it is approaching. Current measurements place its velocity toward the Milky Way at approximately 110 kilometers per second. A speed that, maintained over the timescale involved, will bring the two galaxies into collision in approximately 4.5 billion years. The word collision here is somewhat misleading because galaxies are mostly empty space. When two spiral galaxies collide, individual stars almost never physically impact one another. The distances between stars within each galaxy are simply too vast for direct collisions to be statistically likely. What happens instead is a gravitational disruption of both structures. The spiral arms pulled apart and distorted tidal streams of stars flung into intergalactic space, the central regions of both galaxies eventually merging into a single, elliptical galaxy that astronomers have already named Milky Way or Milkdromeda. The Sun will still exist when this happens. 4.5 billion years from now, the Sun will be approaching the end of its main sequence lifetime, but will not yet have expanded into the red giant phase that will eventually render Earth uninhabitable. Whatever, if anything, exists on Earth or its vicinity at that point will witness the slow-motion spectacle of another galaxy filling an increasingly large portion of the sky over millions of years. The merger unfolding on timescales that dwarf any biological generation. The local group itself, all 54 galaxies across 10 million light-years, is a component of a vastly larger structure. The Laniakea supercluster, identified and named by a team led by astronomer Brent Tully in 2014, using data on galaxy velocities and gravitational flows, contains the local group along with roughly 100,000 other galaxies, spread across a volume approximately 520 million light-years in diameter. Laniakea, the name comes from Hawaiian, meaning immeasurable. Heaven has a total mass estimated at 10 to the power of 17 solar masses. Written differently, 100 million billion times the mass of the Sunday. The local group, which itself contains the Milky Way with its hundreds of billions of stars, is a minor substructure within Laniakea, a small cluster near the outskirts of a supercluster that contains 100,000 galaxies. Every galaxy in Laniakea, including the Milky Way, is moving, and the motion is not random. The velocities of galaxies across the supercluster, when analyzed and mapped, reveal a coherent flow streams of galaxies converging toward a point, a region of anomalously high mass concentration, pulling everything in the supercluster toward it. This region is called the Great Attractor, and it sits approximately 250 million light-years from the Milky Way in the direction of the constellations Centaurus and Hydra. The Great Attractor is pulling the Milky Way and the entire local group and thousands of other galaxies across the supercluster at a speed of approximately 600 kilometers per second, not relative to any local reference frame relative to the cosmic microwave background, the closest thing available to a universal rest frame. 600 kilometers per second towards something massive enough to organize the motion of structures containing trillions of stars across hundreds of millions of light-years. The problem is that no one has clearly seen it. The Great Attractor sits almost exactly behind the plane of the Milky Way's disk, from Earth's vantage point, in what astronomers call the zone of avoidance, where the density of gas, dust and stars in the galactic plane blocks optical and infrared observation so thoroughly that the region behind it is effectively invisible to most wavelengths of light. X-ray and radio observations have penetrated the zone partially, revealing a massive concentration of galaxies in the region, the Norma cluster, and associated structures. But whether these fully account for the gravitational influence being measured, or whether something even larger lies behind them, remains unresolved. The Milky Way is being pulled towards something that cannot be fully seen at 600 kilometers per second, and has been for the entirety of its existence. There is something almost metaphysical in that fact. The entire galaxy, every star in it, every planet, every living thing that has ever existed on any of those planets, all of it, in motion toward a massive unknown, pulled by gravity across hundreds of millions of light-years toward a destination that observation cannot yet fully characterize. The universe does not ask for awareness of its mechanics. It simply operates them. But even Laniakea, that 520 million light-year structure containing 100,000 galaxies, is only a grain of dust in the picture that comes next. Pull back further. Keep pulling. Past Laniakea, past the supercluster scale, past the distances where individual galaxies become invisible dots and superclusters themselves begin to blur into larger patterns, and something emerges that no one expected to find when the first large-scale galaxy surveys began mapping the universe in 3 dimensions during the 1980s and 1990s. The universe is not a uniform distribution of galaxies spread evenly through space like raisins in a bread. It has structure, enormous, intricate, almost organic-looking structure, an architecture of filaments and nodes and vast empty regions that when visualized looks less like a physics diagram and more like the neural network of a brain or the threads of a spider's web, stretched across a volume so large the mind simply refuses to hold it. This is the cosmic web. Galaxies do not exist in isolation, and they do not cluster randomly. They congregate along filaments, thread-like structures of dark matter and gas, stretching across hundreds of millions of light-years with galaxies and galaxy clusters beaded along them like droplets on a spiderweb in morning dew. Where filaments intersect the densest concentrations, form massive galaxy clusters containing thousands of individual galaxies packed into regions a few million light-years across. Sitting at the nodes of the web where gravitational influence from multiple filament directions converges. Between the filaments and the nodes lie the void's vast regions of space nearly empty of galaxies occupying the majority of the universe's total volume while containing a small fraction of its matter. The cosmic web is not a theoretical construct imposed on data to make sense of it. It emerges directly from the physics of the early universe. Quantum fluctuations in the density of matter in the first fractions of a second after the Big Bang seeded slight overdensities and underdensities throughout space. Gravity amplified those differences over billions of years. Overdense regions attracted more matter, grew denser, eventually collapsed into filaments and clusters. Underdense regions lost matter to their surroundings, grew emptier, became voids. The web visible today in galaxy surveys is the gravitational evolution of quantum noise from the universe's first moments, written in the positions of 2 trillion galaxies across 46 billion light-years. The voids are the feature that most consistently surprises people encountering the cosmic web for the first time. They are not small gaps between clusters. They are dominant features of the large-scale universe, typically ranging from 100 to 300 million light-years in diameter, occupying an estimated 70 to 80% of the universe's total volume. The Botes void, discovered in 1981 by Robert Kirshner and colleagues during a survey of galaxy redshifts, is one of the largest known, a roughly spherical region, approximately 330 million light-years in diameter, containing far fewer galaxies than statistical models of the universe would predict for a volume that size. It is not completely empty. Subsequent surveys have identified a small number of galaxies within it, but compared to the filaments and clusters surrounding it, the Botes void is as close to nothing as large-scale cosmic structure gets. The thought experiment it generates is worth sitting with. If the Milky Way were located at the center of the Botes void, instead of in the relatively well-populated local group within Laniakea, the nearest large galaxies would be 150 million light-years away in every direction. The night sky, already almost entirely empty space, even from Earth's actual position, would be dramatically darker. The nearest galaxy clusters, which appear in Earth's actual sky as faint smudges accessible to moderate telescopes, would be at distances requiring the largest observatories to detect. Crucially, without the evidence of nearby galaxy clustering, without the visible structure of the cosmic web accessible to early astronomical surveys, the inference that the universe has large-scale structure at all would have been far harder to reach. Cosmology as a science might have developed on entirely different assumptions. The understanding of where we actually are structurally in the universe depends partly on the fortunate accident of being located somewhere with enough neighboring galaxies to map. At the opposite extreme from the void sits the largest known structure in the observable universe. The Hercules Corona Borealis Great Wall was identified in 2013 and 2014 through analysis of gamma-ray burst distributions. The brief, intensely energetic explosions that occur when massive stars collapse or neutron. Stars merge visible across cosmological distances and tractivazing, therefore usable as tracers of where galaxies existed at various points in the universe's history. The analysis revealed a statistically significant concentration of gamma-ray bursts in a region spanning an estimated 10 billion light-years in its longest dimension. 10 billion light-years. The observable universe has a radius of 46.5 billion light-years, meaning this single structure, if the estimates hold under further analysis, spans roughly a fifth of the observable universe's diameter. Structures that large sit uncomfortably against the cosmological principle, the foundational assumption that the universe is homogeneous and isotropic at sufficiently large scales, meaning it looks the same in all directions and from all positions when averaged over large enough volumes. The Hercules Corona Borealis Great Wall at 10 billion light-years is large enough that some cosmologists argue it challenges that principle, or at minimum forces a reconsideration of what scale sufficiently large actually means. The debate is ongoing, and the structure requires further characterization, but its existence in the data is not seriously disputed. Against this backdrop of filaments and voids and structures spanning billions of light-years, the count of galaxies in the observable universe needs updating from the number most people carry from introductory astronomy. The figure of 200 billion galaxies, long the standard estimate repeated in textbooks and documentary narrations, was revised substantially upward in 2016 by a team led by Christopher Consolis at the University of Nottingham, publishing in the Astrophysical Journal. Their analysis of deep field imaging from the Hubble Space Telescope, combined with modeling of galaxies too small and faint for current instruments to detect directly, produced a revised estimate of approximately 2 trillion galaxies in the observable universe, roughly 10 times the previous figure. 2 trillion, 2 million. Most of them small, faint dwarf galaxies in the early universe now, too distant and too dim for any current telescope to resolve individually, but present in the data through statistical inference. 2 trillion galaxies. The Milky Way, with its 200 to 400 billion stars and its 4.5 billion years of history, is one of 2 trillion. On the map of the full observable universe, the entire Milky Way, every star in it, every planet, every atom of every living and non-living thing that has ever existed within its boundaries, is smaller than a single grain of sand on a beach, wider than the entire continental United States. Not a metaphor constructed for rhetorical effect. A straightforward consequence of the numbers which do not adjust themselves for human comfort. But even accounting for all 2 trillion of those galaxies, there is still a boundary that physical light cannot cross, and what lies behind it is the largest open question in modern science. The observable universe has a radius of approximately 46.5 billion light-years. That number requires immediate explanation because it contradicts an assumption almost everyone carries. If the universe is 13.8 billion years old, shouldn't the farthest observable point be 13.8 billion light-years away, the distance light could have traveled since the Big Bang? The answer is no, and the reason is cosmological expansion. Space itself has been expanding since the Big Bang and continues expanding now. When a photon was emitted from a distant source early in the universe's history and has been traveling toward Earth ever since the space between the source and Earth has been stretching during the entire transit, the photon arrives having crossed a distance much larger than the simple multiplication of its travel time by the speed of light would suggest, because the destination moved farther away while the photon was en route. The 46.5 billion light-year radius is the current distance to the most distant observable sources, accounting for that expansion. The farthest thing that can be observed is not a galaxy. It is not a star. It is a wall of light, the cosmic microwave background radiation, the CMB, and it represents a fundamental physical limit on observability that no telescope, regardless of its size or sensitivity, can penetrate. In the first moments after the Big Bang, the universe was a plasma matter so hot and dense that photons could not travel freely. They were constantly absorbed and re-emitted by charged particles, making the early universe opaque in every direction. As the universe expanded and cooled approximately 380,000 years after the Big Bang, the temperature dropped to the point where electrons could combine with protons to form neutral hydrogen atoms. This transition, called recombination, removed the charged particles that had been scattering photons. For the first time, light could travel freely through space. The photons released at that moment have been traveling ever since, their wavelengths stretched by the expansion of space from visible light to microwave radiation, arriving today as the cosmic microwave background, a nearly uniform glow of microwave radiation coming equally from every direction in the sky, carrying a snapshot of the universe as it existed 380,000 years after its beginning. The CMB is the oldest light in the universe. It is also, in a precise physical sense, a wall. Looking outward toward it is looking back in time to the moment the universe became transparent. What lies beyond it, the plasma state of the universe before recombination, is not dark in the sense of being hidden by distance or obscured by dust. It is causally inaccessible. The universe was opaque. No photon from that era survived to reach Earth. No electromagnetic observation of any kind can see through the CMB to whatever structure existed before it. The James Webb Space Telescope, operational since 2022, has pushed observational astronomy to distances and look-back times previously unachievable. Webb is designed to detect infrared light, the wavelengths into which visible light from the very earliest galaxies has been redshifted by cosmic expansion, with a sensitivity and resolution that the Hubble Space Telescope could not match. As of recent observations, Webb has identified galaxy candidates at distances corresponding to look-back times of approximately 13.5 billion years, meaning the light detected left those galaxies when the universe was only about 300 million years old. Some early results have identified structures forming earlier than cosmological models predicted, requiring refinement of the standard picture of how the first galaxies assembled. 13.5 billion light-years. That is approaching the practical limit of electromagnetic observability, not quite at the CMB wall, which sits at 380,000 years after the Big Bang, rather than 300 million years, but within striking distance of the era when the first stars and galaxies were igniting, in a universe that had been until that point completely dark. The expansion of space introduces a further constraint beyond even the CMB. The universe is not just expanding, it is accelerating in its expansion, driven by dark energy, a phenomenon whose nature remains one of the deepest unsolved problems in physics. Galaxies sufficiently distant from Earth are receding faster than the speed of light, not because they are moving through space faster than light, which special relativity prohibits, but because the space between them and Earth is expanding fast enough that the combined recession velocity exceeds light speed. This is permitted by general relativity, which constrains the speed of objects moving through space but places no limit on the rate at which space itself can expand. The consequence is permanent inaccessibility. There are galaxies that exist right now, galaxies with stars, potentially with planets, potentially with whatever they contain, from which light emitted today will never reach Earth. The expansion of space between those galaxies and this one is already outpacing the speed at which that light travels. The light will be moving toward Earth forever, and the distance will be growing faster than it can close. Those regions of the universe are not merely far away, they are permanently, irreversibly beyond any possible future observation or contact, regardless of how advanced the technology doing the looking becomes. The observable universe, the sphere 46.5 billion light-years in radius, is not the universe. It is the portion of the universe from which information has had time to reach Earth, and from which information can still, in principle, arrive. The actual universe may be vastly larger than this sphere, and the portion beyond the observational horizon is not empty or non-existent. It simply cannot be seen, measured, or interacted with from here. But the observable universe is only what physics allows to be seen, and the question of what lies beyond it leads to what may be the greatest discovery or the greatest mystery in the history of science. Everything encountered on this journey so far, every layer of atmosphere, every radiation belt, every planet, every star, every galaxy, every filament of the cosmic web, every structure, from the troposphere to the edge of the observable universe, belongs to a single category of reality: ordinary matter, baryonic matter, the stuff made of protons, neutrons, and electrons, the atoms that compose every object ever touched. every instrument ever built, every photon ever detected by any telescope humans have ever pointed at the sky. That category accounts for 4.9% of the universe. Not 49, not 4.9 out of 10. 4.9% of everything that exists by the best current measurement available to physics. The data comes from the Planck mission, the European Space Agency's space observatory, that mapped the cosmic microwave background radiation with unprecedented precision between 2009 and 2013, producing the most detailed picture of the early universe ever constructed, and as a pride consequence, the most accurate accounting of the universe's total composition. The numbers from that accounting have not been seriously challenged since their publication. Ordinary matter, 4.9%. Dark matter, 26.8%. Dark energy, 68.3%. The entire visible universe, every star, every galaxy, every nebula, every black hole, every atom of hydrogen in the interstellar medium, every molecule of water, in every ocean, on every potentially habitable planet, in every solar system across 2 trillion galaxies is a 5% minority in its own existence. The dominant components of reality are things that cannot be seen, cannot be directly detected, and whose fundamental nature remains in the most honest scientific language available unknown. Dark matter was not invented to explain something exotic. It was demanded by something mundane: galaxies rotating wrong. In the 1970s, astronomer Vera Rubin and her colleague Kent Ford measured the rotation curves of spiral galaxies, the relationship between orbital speed and distance from the galactic center. Newtonian gravity makes a clear prediction. Stars far from the center of a galaxy, where most of the visible mass is concentrated, should orbit more slowly, just as the outer planets of the solar system orbit more slowly than the inner ones. Instead, Rubin and Ford found that stars in the outer regions of spiral galaxies orbit at roughly the same speed as stars much closer to the center. The rotation curves were flat where they should have been declining. The only explanation consistent with the physics was that there was substantially more mass in and around the galaxy than the visible stars and gas could account for, mass distributed in a roughly spherical halo extending well beyond the visible disk, exerting gravitational influence without emitting, absorbing, or reflecting any light. Dark matter does not interact with the electromagnetic force at all. It does not emit light. It does not absorb light. It does not reflect light. It passes through ordinary matter without interaction, through planets, through stars, through human bodies, through the most sensitive detectors ever built, without leaving a signal. The only force through which it makes itself known is gravity. It is the invisible scaffolding of the universe, the structure along which the cosmic web's filaments form the mass that holds galaxy clusters together against velocities that would otherwise scatter them, the gravitational glue that kept the Milky Way from dispersing across intergalactic space long before the first star ever formed within it. Without dark matter, the universe as observed, the galaxies, the clusters, the cosmic web, could not exist in its current form. With it, the structure of the observable universe falls naturally out of the physics of gravitational collapse applied to the initial density fluctuations. The model works. The substance itself has never been directly detected. Dozens of experiments over decades have searched for dark matter particles. Underground detectors in mines in South Dakota, in Italy, in Canada, laboratories buried beneath kilometers of rock to shield them from cosmic rays, lined with the most sensitive particle detectors ever constructed, have looked for the faint signal of a dark matter particle colliding with an ordinary atomic nucleus. The Large Hadron Collider at CERN has searched for dark matter production in high-energy particle collisions. Space-based instruments have looked for gamma rays that dark matter particles might produce when they annihilate each other. The results across all these approaches have been constraints rather than detections, increasingly precise statements about what dark matter is, not without a confirmed statement of what it is. Dark energy is a different problem entirely, and in some ways a deeper one. In 1998, 2 independent research teams, one led by Saul Perlmutter at Lawrence Berkeley National Laboratory, the other led by Brian Schmidt and Adam Rias, were studying type Ia supernovae, a class of stellar explosion useful as a standard candle because their intrinsic brightness is well understood, making them reliable distance indicators. Both teams were attempting to measure the deceleration of the universe's expansion, the expected slowing caused by gravity pulling matter back together after the Big Bang's initial outward push. What both teams found instead was that distant supernovae were fainter than expected, meaning they were farther away than the models predicted, meaning the universe's expansion was not slowing down, it was speeding up. The discovery was so unexpected that both teams spent considerable time checking for systematic errors before accepting what the data showed. The expansion of the universe is accelerating. Something is pushing space apart at an increasing rate, overcoming gravity at the largest scales, driving galaxies beyond the observable horizon at velocities that will only increase with time. That something carries the name dark energy, and the name is almost entirely a placeholder, a label attached to the phenomenon because the phenomenon clearly exists and clearly requires a name, not because the name conveys any understanding of what it actually is. The leading theoretical candidate is the cosmological constant, a term Einstein introduced into his field equations in 1917, then withdrew after the expansion of the universe was discovered, famously calling it his greatest blunder. In the framework of quantum field theory, empty space is not truly empty. It has an energy density arising from quantum fluctuations, a vacuum energy that acts as a repulsive force at cosmological scales. The cosmological constant, interpreted as this vacuum energy, can mathematically reproduce the observed acceleration. The problem is that when physicists calculate the predicted magnitude of vacuum energy from quantum field theory and compare it to the observed magnitude of dark energy, the two values disagree by a factor of approximately 10 to the power of 120. This is the largest discrepancy between theory and observation in the history of physics. The prediction is wrong by more orders of magnitude than there are atoms in the observable universe. Something is deeply incomplete in the understanding. The ESA's Euclid telescope, launched in July 2023, is currently mapping the distribution of galaxies across 10 billion light-years of cosmic history, with the specific goal of constraining the behavior of dark energy over time, whether it is truly constant or whether it varies, which would distinguish between different theoretical models. NASA's Nancy Grace Roman Space Telescope, planned for launch in the 2026 to 2027 timeframe, will complement Euclid's survey with its own wide-field infrared imaging, adding dark matter lensing maps and supernova distance measurements to the dataset. These two observatories represent the largest coordinated scientific effort in history, aimed at a single pair of problems, and the answers they return will either confirm the current model or break it in ways that force a fundamental reconstruction of physics. What deserves more weight than the known facts is a simpler observation. Physics can describe the behavior of dark matter and dark energy with reasonable precision. It can predict where dark matter must be present from galaxy rotation curves and gravitational lensing. It can measure dark energy's effect on the expansion rate with increasing accuracy. What it cannot do, what no one has yet managed, is say what either thing actually is. Not in the sense of a fundamental description. Not in the sense of identifying the particle, the field, the mechanism. 95% of the universe, the absolute majority of everything that exists, remains a question without a confirmed answer. Modern science is not a finished book. It is an enormous stack of blank pages with a small dense section at the beginning that has been written with extraordinary care and precision, and an expanse of white that dwarfs it entirely. And now, after a vertical journey that has passed through every layer, from 12 kilometers of atmosphere to 46 billion light-years of observable universe, there is one final question whose answer will make the entire journey just traveled feel small one more time. This entire journey rested on an assumption so deeply embedded it was never stated. The assumption was that above Earth means something, that straight up is a direction fixed, coherent, pointing somewhere specific, the way north points toward the pole or east points toward the rising sun. The whole journey proceeded as if the vertical line from the surface extended outward through a stable geometry, passing through layers and distances and structures, all of it oriented along a single meaningful axis. That assumption is wrong. In four-dimensional spacetime, the framework that general relativity established as the actual geometry of the universe, confirmed by every precision test physics has subjected it to for over a century, there is no absolute up, there is no absolute down. Direction is not a property of space itself. It is a relationship between an observer and their local environment, and it depends entirely on three things: position, velocity, and time. All three are changing continuously without pause. For every point on Earth's surface, the planet rotates. It orbits the sun moves through the galaxy moves within Laniakea. Laniakea falls toward the Great Attractor. The entire observable universe expands in every direction simultaneously. Above your head right now is not a line pointing somewhere fixed in space. It is a vector that changes every fraction of a second, tracing through the solar system, the galaxy, the local group sweeping through coordinates that no static map can capture, because the map itself is in motion relative to every possible reference frame. The journey taken was real, the layers are real, the distances are real. The structures are real, but the premise of a single fixed above was a convenient fiction maintained for the purpose of traveling through it. A useful illusion. The universe does not actually have a ceiling. Now consider what lies beyond the observable boundary just reached. The observable universe, the sphere 46.5 billion light-years in radius, containing 2 trillion galaxies structured into the cosmic web, pervaded by dark matter and dark energy, bounded by the wall of the cosmic. Microwave background is almost certainly not the whole universe. The theory of cosmic inflation, first proposed by Alan Guth in 1980 and developed substantially since, describes a period in the universe's first fractions of a second during which space expanded at an exponential rate driven by a high-energy field that caused regions of space to double in size repeatedly in extraordinarily short intervals. Inflation lasted for an extremely brief period before ending and transitioning into the slower expansion observed today. But, in that brief period, it stretched the universe to a scale that dwarfs the observable portion by a factor that numbers struggle to represent. The inflationary models predict that the total universe, the full extent of space, not just the portion from which light has reached Earth, is larger than the observable universe by a factor of at least 10 to the power of 23, that is 100 million times larger. Some versions of inflation predict a universe not just vastly larger, but genuinely infinite in extent. The observable universe, with all its 2 trillion galaxies and 46 billion light-years of radius, would then be an infinitesimally small bubble within a larger space, so vast that the word vast loses all semantic content. And inflation may not have ended uniformly everywhere. In the model called eternal inflation, the field driving exponential expansion continues in some regions of space, even as it ends in others, producing a permanent, ongoing generation of bubble universes, regions where inflation ends and local physics establishes itself, each bubble potentially with different physical constants, different particle masses, different laws. The Milky Way, the observable universe. The entire structure just traversed from troposphere to CMB wall. All of it, a single bubble in an eternally inflating space, generating new bubbles without cessation. String theory, the leading candidate for a unified description of quantum mechanics and gravity, independently arrives at a similar conclusion through different mathematics. The theory's landscape of possible solutions, the number of distinct ways its extra dimensions can be compacted into the four-dimensional spacetime observed, is estimated at 10 to the power of 500. Each distinct solution corresponds to a universe with different physics. If all those solutions are realized, above, from any point in any one of them, does not lead merely to another location in that universe's space. It leads in some sense that current mathematics can gesture toward, but not fully describe to a configuration space, the space of all possible physical laws and initial conditions that no existing mathematical language is equipped to map. The question of what is directly above Earth extended to its logical extreme arrives at the boundary of what mathematics itself can currently address. Look straight up one more time. Blue sky, white clouds. The same familiar dome that has been there every clear day of every life ever lived on this planet. Comfortable, ordinary, the sky that children draw and poets describe, and everyone takes for granted as the simple backdrop of existence. But through that layer of atmosphere thinner than an apple's skin, through the ozone shield 3 millimeters thick, through the mesosphere where meteors burn, through the thermosphere where the aurora writes in light the story of the Femme, sun attacking the planet through the exosphere, dissolving into interstellar nothing. Through all of that lies 46.5 billion light-years of matter, radiation, darkness, and mystery. 2 trillion galaxies, a cosmic web of filaments and voids. Dark matter that has never been directly seen. Dark energy whose nature no one understands. A boundary wall of ancient light, beyond which observation cannot reach. And past that boundary, a universe that may be 10 to the power of 23 times larger than everything visible or infinite, or one of an uncountable number of universes in a space that existing physics cannot yet describe. Above is not a direction. It is the entirety of existence, and humanity has only just begun to learn how to ask the right questions about it.